Okay, hello everyone. My name is Devendra Kapadia, and I work here at Wolfram as a kernel developer for DSolve and other functions, Symbolics. I'm basically a symbolic algorithm developer. And over the last year, roughly since the last conference, I've been working on adding support for symbolic solutions of PDEs to DSolve. That's been a long-standing request from many people. We know that we had to do it, and finally we got down doing it last year. And then we shipped 10.0, 10.1, 10.2, in which we had ND Eigensystem, a very nice, beautiful function written by Oliver Rubenkoenig. And so in response to that, I added D Eigensystem to my project. And so today I'm going to speak about DSolve and DSolve Eigensystem in Mathematica 10.3. But I realized that PDEs is a kind of, it's a hard subject. It's something that not everyone works with every day. So I thought that the docs are pretty complete. You can look at them on the web or on product or wherever. And for myself, I'm going to just present to you a small kind of tour through the world of PDEs using Mathematica 10.3. Very simple examples, almost minimal text, and I hope that that'll go down well. Okay, so here's my outline for the talk. So the basic point is that I want to show you brand new examples in version 10.3 for DSolve and D Eigensystem. But the plan is to first take on the classical PDEs, the kind of PD that you would have seen in a first course on PDEs if you ever took one. The wave equation, the heat equation, the Laplace equation. And if we had just done that, people would have been really happy with us. That itself is quite a lot. But then I realized that in modern times, PDEs have moved on. And so I took three examples for today's talk. The first one is Berger's equation from fluid dynamics, which is quite interesting. It's a nonlinear PDE. The famous Black-Scholes PDE from finance, which we all know of from recent events from the last decade or so. And the Schrödinger equation from quantum mechanics, which is probably the most important PDE of the 20th century. So that's my plan for the modern stuff. And then we go a bit deeper into DSolve and look at what are called Sturm-Liouville problems. So these are kind of eigenvalue problems for ordinary differential equations. Again, that's been a major problem for us to solve for a number of years. We have now cracked it completely, I think, at least for the second order ODE case. And that'll be the third topic for today's talk. And finally, I'll talk about D Eigensystem in relation to differential operators. So it's a very simple plan for the talk. Let's begin with the wave equation. That's the first classical PDE. Very simple PDE. So here's the problem. You want to solve the equation, which I've stated over here, the wave equation. It just says second partial with respect to time of a function is equal to second partial with respect to x. So to solve it, you give some initial condition. So you think of giving a pulse of some kind. You give the pulse over here. And then after that, you call DSolve, and that's a pretty simple equation to solve. In fact, it was solved by D'Alembert several centuries ago, and that's the solution. So the first part over the exponential terms are coming from the initial condition over here, and the t is coming from the initial velocity. Okay, so having got the solution, I now plot it, and that's a nice plot. But at this point, I should say that the wave equation is a basic, it's a fundamental example of what we call a hyperbolic PDE. So what are they? Well, a hyperbolic PDE is one for which, first of all, the initial value is problem is well posed. So you give initial values, the PDE knows what to do, and it goes and solves itself. Okay, like a universe is driven by hyperbolic PDEs. So you create it, and then it goes. Okay, the second point is that over here, you have finite propagation speed. So if you're a long way out on this infinite string, then it's going to take a longer time for the pulse to reach you. The third point is that you can see that there are really these two directions over here, which are called characteristic directions, and the PDE kind of evolves along those two directions. And that's why it's called hyperbolic, because there are two of them, not just one. And one last point, that if you have initial data which are smooth, then the solution itself is smooth. And conversely, if you have sharp initial data, then the solution itself is not smooth. And that's, of course, what you expect in the real world. You expect your signals not to get distorted as time goes by, so that's perfect. Okay, so that simple example actually captures everything you want to know about hyperbolic PDEs. And I could stop over there, but then you'll tell me, oh, but real strings are not infinite length, so what happens over there? Well, things become a lot more complicated and a lot more interesting. So here's a vibrating string. That's the first time you can actually do it in Mathematica without any work by hand. So that's the wave equation. You must specify that the string is fixed at both the ends. And in modern terms, you say that's a homogeneous Dirichlet condition. I must get some kind of an initial pull. So I pull the string at some point and let it go. And then I give it a desolve. And this takes a bit of time on this laptop, around 32 seconds if I remember it right. But what's happening over here is it's calling a sequence of methods. We have layered the code in such a way that we actually try different methods, and occasionally we might actually have to give up because the solution is not the right quality. My worry is not people who are experts, but people who are doing, let's say, a first course on PDs. They use desolve, they get something that they don't really like, so I want them to get just the right solution. So it takes a bit of time, but when it's done, you actually get what one would see in a typical textbook on PDs, and that's the solution coming from what is called separation of variables. So that's the solution, and in version 10 we had inactive, so that sum over there is inactive. Do ask questions if you have to, but that sum is an inactive sum. It doesn't do anything until I activate it. And that looked to me like the right thing to do because in textbooks, people don't actually try and evaluate that kind of sum. Okay, so now I must pull out some stuff from the inactive sum. So I take the first 4 terms and I activate, and what you see over there are some simple solutions of the wave equation. Each term over there is a solution of the wave equation. It's, in mathematics, you would say it's separation of variables. In physics, you would say they are standing waves. In linear algebra, you might say they are eigenfunctions, but that's all the same thing. They are exactly the simple solutions which make up the solution of the wave equation in this case. So let's plot them, and you see a typical Halliday and Resnick kind of illustration over here with the standing waves for the wave equation. And it's a miracle of Fourier analysis that you can put all these together, and when you actually run the animation over here, then the string vibrates smoothly based on the sum of all those eigenmodes. So this is something that's kind of automated now, very easy to do. You can do it for a string, you can do it for a drum, it's all documented, and I hope that people will find it useful. So that's about the wave equation, and now we move on to the second example for today, which is the heat equation. So over here you have, that's the heat equation, first partial with respect to t equal to second partial with respect to x, and then you give an initial condition, which I, in this case, take to be piecewise. It's a box function. But you know that when heat spreads out, it spreads out quite evenly. So if I solve the equation over here, then the solution which you get back is in fact going to be not quite piecewise. In fact, it's an error function solution. So if I plot it, then what you get is a nice and smooth solution. So the flow of heat simply makes everything nice and smooth instantly. The second point is we have an initial value problem, which is solved nicely. So the heat equation is an example of a parabolic PD. So we have parabolic PDs, but if you know the heat equation, you know them all basically. And you'll see later on that the heat equation is of supreme importance in mathematics. Okay, so you'll tell me now that, oh, that's an infinite bar. In the world, bars are not infinite. So here's a finite bar. You've got a bar of, let's say, iron or whatever. You want heat to flow through it, but you would like that the, okay, so here's the heat equation again. Now you want the bar to be insulated at both the ends. That's my condition for this one. So I say the derivative on both the sides is 0. And technically, that's called a Neumann condition. Okay, and a Neumann, N-E-U-M-A-N-N. That's German. I guess Neumann, right? Anyone German from here? Yes, right. Okay, this Hungarian. I'm sorry.
Well, I mean, it's German, but he was Hungarian.
Oh, he was Hungarian. Yeah, I see. Oh, okay, right. I guess it means Newman. Is that thing? Okay, so there's Dirichlet and Neumann. Okay, right. Dirichlet's boundary, and this is fixed derivative. Okay, now the initial temperature over here is rather simple. Okay, and what you see is that at the left end, the temperature is 20. At the right end, the temperature is 100. Okay, so what's going to happen as time goes by, it's all going to become 60 if it's a nice regular kind of bar. And so if you solve the equation, that's exactly what we do internally. We figure out the steady state solution, and when you see a solution, it will have exactly what you expect it to be. So that's also separation of variables in this case. And for the heat equation, we have several methods, but it will definitely do the right thing for this kind of simple example. So the first term over here is the steady state solution, and everything else is the separation of variables from the higher modes. Okay, so now you take a few terms, and then each term is again a solution of the heat equation. Sure?
Question, why didn't you use formal variables in the sum? Why use an artificial constant?
Like what?
You could have used a formal variable.
I'm using them for eigenvalue problems. I'll see it later.
Okay.
But I'm happy to change that. I mean, I would have loved to. Yeah, right. Okay. I did what would kind of pass review, you know. Okay, so, right. Okay, I picked up as much courage as I could and then did this. Okay, so now if you plot the solution, you see that initially it's that blue line over there is the initial state, and then very quickly the bar balances out, and you get the steady state solution at 60 degrees centigrade or whatever. Okay, so that's the second equation. And now the third equation is the Laplace equation, which is by far the hardest to solve. It took 25 years or whatever for ND Solve to learn how to do it. And we've taken 26, so we're not doing that badly over here. But here's the Laplace equation. Ask eta, he'll tell you that's Laplace in equal to 0. Okay, you give some boundary conditions. Now there's no time, so no initial conditions. You solve the problem, and things go a lot faster. You know why? Because we don't know much about the Laplace equation, so we don't have that many methods, so things go really fast. We just go up everywhere and then we come to the right method. But what you get back is, again, a separation of variable solution. But by now you know the routine, so you pick 300 terms, no harm, and you plot it. And what you see now, and it's done, is a solution which is very typical of what are called elliptic PDEs. So the Laplace equation is the standard example for an elliptic PDE. So what's elliptic mean? Elliptic means that first of all, you must give boundary values. That's why you have all this region functionality in version 10. Secondly, the solution becomes instantly smooth. It's like a steady state, so everything is nice and smooth. The corners at the end. And thirdly, all the maxima and minima are on the corners. There's nothing in the middle, which is a maximum or a minimum. So that simple example captures everything about elliptic PDEs. Okay, now in version 10 we have the region functionality, and we have ND Solve, which does PDEs over regions in a wonderfully, it's a dramatic improvement over there. So the question was, can we do the same for D Solve? No, historically, people think of D Solve and ND Solve and they never meet. Okay, but we said let's try and see if we can meet ND Solve in some way or the other. So here's the Laplace equation again, but now I have more modern notation. I talk about Dirichlet condition instead of boundary condition. The same problem. I have a rectangle for the domain, and now with a slightly different notation from traditional, I say x and y belong to the rectangle. And you solve the equation, and hopefully you'll just get back the same solution. Okay, so then you again check that you've done the right thing. So let's just quickly go through that. Check this, check that, and we are done. Okay, now the nice thing over here, at least to me, is that almost for the first time, you can go to the DSolve over here and simply put an n in front, and it goes and calls the FEM code and gives back the numerical solution. So DSolve has essentially got the same syntax now as NDSolve, at least in these simple examples. And generally speaking, if you try an NDSolve example or DSolve example, you can flip notation quite easily now, which is a good thing in the long run. Okay, so that's the classical PDEs, and now we go on to more modern stuff. So the first problem is Berger's equation. Now, Berger's equation arose in J.M. Berger's study of turbulence, and turbulence is a great problem. Everyone's worked on it. John Nash wrote a paper on it called Parabolic PDEs, but if you look at the paper, it's about turbulence. So everyone who's anyone worked on turbulence, and the simple truth is all of them failed so far, okay? So J.M. Berger's in the 1950s thought he had cracked the problem. So instead of the Navier-Stokes equations, which are horribly complicated, he had this wonderfully simple quasi-linear PDE to solve. He was quite happy about it. But if you work in turbulence, the last thing you want is someone to tell you that your equation has got a closed form solution. And 10 years later, Hopf and Cole told him that your equation is nothing but the heat equation. And all hopes were drowned for Berger, but that equation continues to be important, so that's why it's good to study it. So that's the initial condition I take. I take a piecewise initial condition, but keep in mind you are in the parabolic domain, so that's not going to matter. I give it a d-sol value so you can admire the formula when it comes out. So you hand it off to integrate and sit back and enjoy the flight while integrate does all the work. So it takes some time. This is a hard integration, but it does succeed. So it's the Berger's equation with a piecewise initial condition. And essentially the course close to, yes, sure.
A quick question. When were these solutions introduced to Mathematica? Is it
10.3. Everything I'm saying today isn't 10.3. It never worked before.
10.2 is not?
No.
Yeah, that's what
It's all fresh.
Okay.
Yeah, right. I mean, it worked on my machine, but not every. Okay, yeah. So, and I mean, I'm trying to give an introduction to what's there, and every example in this talk is new. There's nothing that worked early on.
Is it already part of the documentation?
Yes, I can show you documentation in a minute. In fact, it's very nicely documented, I think. So if you go to dsolve page, in fact, we wrote the whole dsolve page just for this project. So starting from the top, everything is new. And if you go down to, that's a good question, thank you. You go to the scope section, and there are sections, maybe I should enlarge a little bit. Okay, so there's stuff on hyperbolic PDEs, parabolic PDEs, elliptic PDEs, general PDEs, PDE regions. There are applications, there's drum oscillations, all kinds of stuff over there. So it's pretty complete, the documentation over here. Okay, so we've found a solution over here, error functions. I plot it, and it's nice and smooth. Now, I know nothing about fluid dynamics, so I asked Paritosh Mokasi, is that reasonable? He said it's reasonable, but when you go to the limit as epsilon goes to 0, the viscosity goes to 0, then you start seeing some interesting behavior. So what you're seeing over here is that you have solutions of the Berger's equation, and as the viscosity goes to 0, they develop something called a shock discontinuity, which is well known for a long time. But now you can see it in Mathematica without any work. Okay, so the second example for today is the famous Black-Scholes equation, which is come from finance. So around 1973, Black and Scholes wrote a paper which has been cited 28,771 times as of today. And they gave us one equation which they believed cracks the whole problem of pricing options. Okay, so that's the master model from Black-Scholes. Now let's not worry about what everything means. I'm not a finance person. There is at least one person over here who is. But the point is that in their original paper, Black and Scholes said, look, this equation is nothing but the heat equation in disguise. So they gave a formula for transforming into the heat equation. So, but we know the heat equation quite well. We can solve it. So I do that over here. And you get back the famous Black-Scholes formula from Mathematica. By the way, the interesting problem over here is to find the value at some later period of time. It's usually called the expiry date for the option. So that's the capital T over here. Okay. So then you give some typical values, and you get back a number. Question, what does it mean? Well, I didn't know that much myself, but then I called finance derivative, which is a built-in function, and that tells you that I'm solving a vanilla European call option model. The K in my model is a strike price, the price at the end of the period. The expiration time is 1. The interest rate for a comparable asset which you just put into the bank or whatever is 0.05, etc. And financial derivative actually confirms for me that the answer is exactly the same. Okay, so it's nice to have DSolve doing finance. Okay, so having done finance, we now move on to quantum mechanics. And at this point, I kind of was out of my depth, so we called him Itai Segev, who actually is a physicist, and he implemented the Schrodinger equation. Okay, so that's the Schrodinger equation. We want to model the electron in a box problem. So you want the electron not to leave the box. That's a homogeneous Dirichlet condition. I get some initial conditions over here, which is simple enough. I solve the equation and get back a nice solution. Does that come from Fourier transform, Itai? Is it?
Well, it's a kind of Fourier series, essentially.
I see.
It's a Fourier sine series.
I see. But you're actually doing a series and then getting the solution from there. Okay, fine. Okay, now Max Born taught us that if you want to study quantum mechanics, don't worry about psi, worry about the probability density. So we actually do psi times the complex conjugate, and you get back a probability density. We plug in parameter values. So it's an electron, that's the electron mass. That's the box, it's a very small box, very tiny box. And then run an animation, and you can see that the electron goes from side to side in the box, oscillating back and forth between the two ends. It's this kind of nice demo example that makes the new functionality really interesting, that we can see all these things so clearly without much effort. Okay, now over the years, we have had an issue with what are called eigenvalue problems. So these eigenvalue problems are very simple differential equations, but they are very hard to solve. Okay, so here's an example. They're called Sturm-Liouville problems technically. So you have y double prime plus lambda times y equal to 0. That's easy. It's either sine or cosine. But then you want y of 0 equal to 0 and y of pi equal to 0, for example. Now, these equations always have a trivial solution. But sometimes, for some values of lambda, they also have interesting solutions. And we would happily return 0 for many versions, and people complain, and we just kind of, look the other way. So, but now we can actually solve the problem, and we give back what people expect. We give back the eigenvalues. In this case, the eigenvalues are the squares of natural numbers. And Paul, that answers your question about why we didn't use the formal n. Because formal n is used over here. So we're using it to parameterize the eigenvalues. But I agree with you, it would be nice to have them elsewhere. Okay, so the eigenfunctions you can pull out by giving values to the lambda parameter, and you can plot them, and you get back this beautiful plot of the eigenfunctions.
Excuse me.
Huh?
Could you explain the notation?
Sure. Okay, so
And with the dots?
sure. Okay, so that's an eigenvalue problem. Lambda is a parameter. It only has solutions for fixed values of lambda. The n is a formal variable from Mathematica. It's slash formal n. The advantage is it can't be assigned values by some, well, hopefully people will not do much with it. So it just looks like a textbook n, but we cannot use n internally. We are not allowed to, so to speak. Okay, so it's an n from a textbook, basically, in Mathematica form. Okay, so now the problem was that when you go to harder problems, then things really do get out of hand. So here's an example with what we call a Robin condition. So that's a Robin condition. It's a mixture of y and y prime. And what do you do over here? Well, we are really stuck because to find the eigenvalues is very difficult. There are infinitely many of them, very difficult to find. So what we do is we simply give back the eigenvalue equation over here. Okay, then if you look at a typical textbook on differential equations, they will then try and solve the equation by plotting and they'll find that, oh, there are two roots between 4 and 10, but we can't do that, so we want to automate everything. And so for that reason, we introduce the assumptions option into version 10.3. So if you say assumptions 1 less than lambda less than 10, then you get back exactly the same solution. So you get two eigenvalues, one at about 4.5, the other one at 7.7. So you can pick your eigenvalues by focusing on a particular small subset of the real line. But this requires a lot of technology from transcendental roots and other places. Okay, so it's not quite non-trivial over here. Okay, on to the last part of my talk, which is about eigensystems. So we have two new functions, d eigensystem and d eigenvalues, which are blatant, more copies or whatever of nd eigensystem and nd eigenvalues. They have the same notation, but basically, if you give d eigensystem an operator and a condition, and you ask it to find, let's say, the first 4 eigenfunctions, eigenvalues, it will go and do that for you in exact form. And then you can plot the results quite easily. Okay, so here you are. The plot is over here. And if you want only the eigenvalues, then you can get the eigenvalues right over here. And the nice thing is, once again, I can replace the d eigenvalues by nd eigenvalues. Simply put an extra n, and you get back the numerical values from nd eigenvalues. So the notation is parallel to that of nd eigenvalues, and actually the functionality is also roughly the same. But of course, beyond a point, the numerics just takes off, and we don't have a chance of getting closed form solutions. So as my last example, and just to show you that things can get really hard but also quite pretty, let's look at the Laplacian in a ball. So that's the Laplace equation, the Laplace operator in 3 dimensions. I say I want Dirichlet boundary conditions, that's 0 on the boundary. I'm working on a ball, like the eigenvalues and the eigenfunctions. These are known in the literature. There are just a handful which are known in the literature. And in one case, there's a whole book written on just one particular set of eigenfunctions. So the problem is quite hard over here, actually. So we are trying to work out the eigenfunctions for the Laplacian in a ball. It takes a bit of time because we need to sort things out. And then to see what they look like, let's just take one of them. That's good enough for a talk of this length. And I call the new function density plot 3D, a very nice function from visualization. And I let it go. On a laptop like this is a hard problem because the function does use a lot of memory, but it should finish up quite soon. But you get really pretty pictures of these eigenfunctions. At least I haven't seen them before in Mathematica or elsewhere easily. But now you can plot them. So it's plotting now. And when it's done, you should see that you actually can picture the eigenfunction quite nicely. So density plot 3D really pictures things in 3D as colored densities, basically. So that requires a lot of effort, but there you go, that's the eigenfunction. So I think that's quite pretty to come from dsolve. Okay, so I'm done. And the main point I want to make is that version 10.3 actually introduces a new framework for solving PDEs. And from now on, if someone said implement X class of PDEs, we can do it quite easily without any problems. But what we have done now could not have been possible but for the developments in visualization, numerics, and in symbolic computation. In fact, we've been writing lots of these super functions over the last few releases, and we can do it with some confidence without breaking everyone's examples. So far, no one noticed any problems with dsolve, which I regard as a healthy thing. Okay, but the main point to me is that we have actually addressed a very large number of requests from our users, whether it be Stephen Wolfram himself, manager of QA, Stack Exchange. I have emails from everyone, and I just hide my face and say, no, we can't do it at the moment, But now, with a straight face, we can, tell me, just try Mathematica 10.3 and we are done. But believe me, it's kind of taken a big burden off me to have to say that we can't do these things. So on that note, I'll stop. But before I do that, here is a summary of today's talk. So we learned about hyperbolic PDEs, parabolic PDEs, elliptic PDEs, modern PDEs, and eigenfunctions. So